Have you ever looked at a computer and wondered what makes it function? What is inside of it? How does it work? I have. And that's why today I will show you how I created my own computer. Not only that, I will take you through the creation process of a new digital circuit, which will interface with a processor to create audio, video, and more. We will go back, blending the old with the new, using a 6502 processor with a modern FPGA to not only build a computer from scratch, but also create new functionality through digital design. This is a schematic that I came up with. You can't have a more basic computer than this. You have the CPU, random access memory, read-only memory, and the header for the FPGA. Let's look at the processor. This is the part of the computer that runs our instructions. The address pins A0 through A15, as well as the data pins D0 through D7, are connected to the rest of the computer. As for the rest of the pins, the res bar input pin is connected to the FPGA header. Here's where we send a reset signal to the CPU by pulsing this pin low. The IRQ bar input pin is also connected to the FPGA header and allows you to send a signal to the processor which stops the processor from doing what it's currently doing in order to handle something immediately. For example, you could have a button connected to this pin. If the button was pressed, this would tell the CPU to stop what it's currently doing to handle the button press. The read-write bar output pin is high if the CPU is trying to read data and low if the CPU is trying to write data. The ROM is the ubiquitous 28C256 32KB ROM. This is where the bootloader and all of our programs will be stored. Whenever the CPU starts up, it will read a memory address from the top of the ROM and start executing code from there. The RAM is also 32 kilobytes. This is where we can store variables, for example, or any data that we will want to modify. This chip right here is a group of negative AND gates, and is where all of the address decoding happens. The address decoding is quite simple. The first 16K of memory points to the RAM. The second 16K of memory points to the FPGA, and finally the last 32K of memory points to the ROM. I also considered moving all of the address decoding to the FPGA, but in order to do that, I would have to send all of the control signals to the RAM and ROM from the FPGA, and I simply did not have the pins. So I went with the simplest decoding I could think of, using only a single NAND gate chip. I had to include a boost transceiver because the ROM and RAM I was using are only rated for 5 volts, while the FPGA can only accept signals of up to 3.3 volts. Therefore, I decided to run the CPU at 3.3 volts as well, and only run the ROM and RAM at 5 volts. Because of this, I had to isolate them from the rest of the circuit. And in order to do this, I used the boost transceiver. Whenever it receives a 5 volt output from either of the chips, it will step it down to 3.3 volts. Thanks to this, the FPGA and CPU are protected. I decided to use the Raspberry Pi header on the FPGA board because there are plenty of pins available here. Of course, we're not connecting to a Raspberry Pi, but to a 6502 computer, but you can configure the pins in the FPGA to do whatever you want. I also added some LEDs in order to see the currently selected address and data lines when running at a low clock speed. To tell you the truth, this is the first PCB I have ever designed, and what you see right now is its first iteration. As you can imagine, there are a few flaws. The biggest of these flaws is that I assumed that when the ROM and RAM are in a high impedance state, that is to say, when neither of them are outputting data through their pins, the bus transceiver would be in a high impedance state as well. This turned out to not be the case, and the bus transceiver needs to be turned off whenever the FPGA is selected by address lines. Because of this, I had to cut some traces and connect botch wires to some pins. Another big problem is the lack of power decoupling for lower frequencies. While running at a lower clock speed, when the address and data LEDs turn on and off, they cause big spikes in the voltage that the FPGA board supplies. If I would have added some capacitors close to the LEDs, that could smooth out their power usage. This is a printed circuit board, and this is the same circuit board but populated and soldered. As you can see, I had to add some botch wires. I also had to add another negative AND chip in order to invert the FPGA selection signal. However, after making these modifications, everything works. Beautiful. Now the board is soldered and ready to be used alongside the FPGA. See you next time when we will configure the FPGA to create a clock signal for the 6502 and we execute a simple program from the ROM.